All right. Okay. We're going to get started here. Hello, this is Dr. Hari Lamba welcoming you to the hydrogen economy. The Hydrogen Training Center of our company, Solar Battery Hydrogen Incorporated, is bringing you this course in basics. This course will not only give you a good understanding of hydrogen, the gas and the fuel, but also give you a good global 360-degree view of its status, prices, and opportunities. We will have presentations by Walter Pyle of Anion Solar Company, and then by myself, Dr. Hari Lamba, for about 40 minutes. And then this will be followed by question and answer session. You're welcome to enter comments in the chat section below. But if you want to ask questions, you need to type them into the Q&A section that appears at the line below. We will answer those questions at the end, and we can consider also possibly a live mode where there could be audio and video communications towards the end. But here, let's introduce ourselves. I'm Dr. Hari Lamba, and I have a PhD in engineering with expertise in materials and mechanical engineering, and then in renewable energy, climate change solutions, and now hydrogen. When I was 12 years, I was trying to play around with the electrolysis of salty water, trying to produce hydrogen. In parallel with my work career, which was mainly in railway locomotives, I ran a company for renewable energy in Illinois for about 10 years that worked on solar PV, solar thermal, vertical axis wind turbines, and ground source heat pumps. Last year, I started a new company, and I've been developing projects since then, and working on innovative technologies, and now this educational activity. Walter or Walt Pyle has a lifetime of experience with hydrogen. His dad, Larry Pyle, and co-workers installed a steam ion hydrogen plant in Berkeley, California to hydrogenate vegetable oils. Larry brought Walt into the plant on weekends while the hydrogen plant was under construction and then operating in the early 1950s. Later, with the USSR's launch of Sputnik, filled the USA's high schools and colleges with the best scientific equipment to catch up in the space race. And there also was an electrolysis of water demonstrator that became available. Following engineering school, Walt worked in the petrochemical R&D field for 30 years and had an office near the largest hydrogen production plant in the world in Richmond, California. Since the 1990s, Walt and his associates at Ion Solar have pioneered small-scale, home-scale hydrogen applications for cooking, heating, welding, cutting, electricity generation, and storage. He has also been conducting R&D in producing green ammonia using solar energy. Now we begin our class with the presentation by Walt, which will be followed by a smaller presentation by myself. Walt, you can now begin your presentation. Go ahead, Walt.
This is the outline of what we're going to cover today. Why hydrogen is important and what it actually is chemically. We'll be talking about how we make it, how we use it, and talking about number 5, fuel cells to make electric power. And we're going to focus on the safe use of hydrogen. Hari will discuss some of the issues about the global status and projections and opportunities. Well, the most common form of hydrogen on the planet Earth is water. And this shows a molecular structure of water. You have 2 hydrogen atoms and an oxygen atom that are in covalent bonding. And hydrogen likes to bond with something else. The actual hydrogen atom, a single hydrogen atom consists of a proton and an electron. It's very unusual to find it as a single atom. Only under special conditions or in outer space would you find it as a single atom. Normally it's bound to something else. In water, it's oxygen. When it's just with hydrogen atoms, they'll bond together and make a hydrogen molecule, which is H2. And the universe probably contains something like 90% hydrogen. But here on Earth, almost all the hydrogen is bound to some other element. And hydrocarbons is currently the common fuel that's used on the planet. And it's also the source of all the carbon dioxide emissions that are climate damaging byproducts of that burning of hydrocarbons. So if there was to be a shift from the use of hydrocarbons to more use of hydrogen, these are some of the significant changes that might be expected. Reducing air pollution and water pollution. When hydrogen is burned in oxygen, the only byproduct is water. And in combustion, that would be water present as vapor, as steam. By shifting to hydrogen more and more, you could expect greenhouse gas emissions to shift proportionally. And in the future, we could have plenty of clean, portable, renewable energy. This is an example of a dispenser that's used to produce or to deliver hydrogen to vehicles. It's a service station dispenser. And this is the kind of new energy that's being promoted worldwide as a replacement for hydrogen in the fuel energy portion of the economy. Well, what is it? It's odorless, it's colorless, it's non-toxic, and non-corrosive gaseous fuel. It could also be a liquid fuel if it's cooled enough. As a gas, it's very light, and any leakage of gas results on the planet of escape upwards into the atmosphere. So it's easily dispersed and taken away from the site where it can be combustible if it's not enclosed. It has a very dense energy content on a weight basis. Here, the comparison would be the weight of hydrogen in kilograms compared to gasoline. And you can see it's very energy dense by weight. However, it's not that dense when it's compared on a volume basis. If you see in 3B, there's less in a liter of liquid hydrogen than there is in a liter of liquid gasoline. For the weight standpoint, yes, it's great for rockets, but as you may have realized, most rockets today don't use liquid hydrogen. They use liquid methane. And the reason for that is because the liquid hydrogen requires a lot of insulation, which adds a lot of weight to the rockets. And with liquid methane, the insulation requirement is much less. It's about similar temperature to liquid oxygen. So SpaceX is using methoxy rockets these days. But back in the Apollo program, hydrogen was the fuel of use. Because the energy density on a basis of weight is similar, such that a kilogram of hydrogen has approximately got the energy content of a gallon of gasoline. And some people will call that a gallon of gasoline equivalent, or a GGE. A hydrogen flame burns hotter but radiates less than natural gas or a hydrocarbon flame because it has no carbon to be the emitter of the heat. To make liquid hydrogen, an enormous drop in temperature is necessary. Minus 252 degrees centigrade or minus 423 degrees Fahrenheit is about 20 degrees Kelvin, or absolute temperature. So it has to be very cold to liquefy it. And to take it from room temperature down to liquid hydrogen temperature requires a lot of cooling energy, and DOE places a value of around 20% of the energy content required to cool it down to a liquefaction temperature. As already mentioned, we find it in water, but we find it also in every kind of hydrocarbon: natural gas, oil, coal, asphalt, heavy fuel, methane, alcohols. All of them have carbon in their formulation. Well, hydrogen burns with a very light blue flame and emits only water vapor, so it's attractive in that way because it can be burned just like a hydrocarbon. To get hydrogen production, the most common form today is by steam methane reforming. That would be SMR by initials. And about 90% of all the hydrogen in use today comes from natural gas and is steam methane reforming. Other ways of getting hydrogen production would be through microbial conversion, through anaerobic fermentation, bacterial conversion. And there is beginning to be a significant amount of biomass conversion, where the first step is anaerobic and forms hydrogen, and the second step is aerobic with air and forms methane. This can come from animal manure and plant debris and other sources of biomass. There are also some direct solar processes that would work through photoelectrochemical means, but most of these are in experimental stages and not at the industrial or large scale. Another way to make it is through electrolysis of water, where electricity is passed through a solution of water. And that electricity can come from any source, but preferably it would be a green source. a renewable source like solar, wind, or geothermal. Hydroelectric would be another example of a green source, both small scale and large scale hydroelectric. The two main processes that account for current hydrogen production would be the steam methane reforming of natural gas. A little bit's done with oil or coal, but not much today. In the turn of the century, between the 19th and 20th century, there was a lot of hydrogen produced from coal by coal steam reforming. And in those days, they called it town gas. And it consisted of hydrogen mixed with carbon monoxide. It was actually somewhat dangerous because of the carbon dioxide content and is no longer practiced because of that hazard. In that day, there was a lot of gas lighting in big cities, 1900 time frame. Today, the steam methane reforming is done by a reformer, and the reformer has a couple of steps to it. The fossil fuel, for example, natural gas, is applied with heat, which is usually obtained from burning more natural gas. And that goes into a first section of a reformer where you produce syngas, a mixture of hydrogen and carbon monoxide. From there, it goes to a water gas shift where more steam is added to that, and it's done over catalysts so that you produce more hydrogen and carbon dioxide. And then the final step is a methanator, which back reacts any additional leftover carbon monoxide to make methane so that there's no damage to catalytic materials from residual carbon monoxide. In the final form, you end up with carbon dioxide and hydrogen, and the carbon dioxide is separated by either pressure swing absorption mechanism or by absorption in amines separators. So that's where most of the hydrogen that's used in the world today comes from. And the primary use of that hydrogen is on-site in petrochemical plants for hydrogenation and hydrogen purification of hydrocarbons. Hydrogenation puts more hydrogen into the hydrocarbon to increase the hydrogen to carbon ratio. And it also is used to remove impurities like sulfur, where you remove it as hydrogen sulfide, and nitrogen, where you remove it as cyanide. In electrolysis, the inputs are only water and electricity. And as previously mentioned, electricity can be from any source. If you put it through the electrolyzer, you end up with two products, hydrogen and the oxygen from the water molecule. And those have to be separated. If there's different electrolyzer technologies, some of the technologies do a better job of separating the hydrogen and oxygen, and some of them do not do as well and require additional purification to make sure that both products are pure. Here are some of the main types of electrolyzers. A proton exchange membrane, an alkaline electrolyzer, and the newer type, anion exchange membrane, and the solid oxide electrolyzers. There's quite a few different companies working with proton exchange membrane electrolyzers. And they use a thin perfluorinated hydrocarbon as the membrane, and it passes protons through it. And we'll get into that a little more detail here shortly. But the membrane is like a solid sulfuric acid that can conduct protons. An alkaline electrolyzer normally uses alkaline electrolyte and not a film electrolyte. It's in a liquid form as a solution of sodium or potassium hydroxide normally. The anion exchange membrane uses a membrane, but it's a much less expensive material, and there's a lot of new players with the anion exchange membrane, and it's an exciting development. The solid oxide electrolyzers run at very high temperatures, and they have a solid ceramic oxide as the electrolyte. As you can see, the steam in one of those electrolyzers has to be at a very high temperature. 700 or 800 degrees C would be typical. Bloom Energy is the company that works with solid oxide electrolyzers. And they're not the most common, but they have their place in standby emergency and fixed power supplies. The ones that are more suitable for use in vehicles would be probably the proton exchange membrane. This is a very nice slide that was obtained from Nell Technology, and they make proton exchange membrane electrolyzers. And I like this slide because it's animated and it shows you what's happening. There's a cathode, and there's an anode, and that is where the electricity is applied. And so if you have your source of electrons out here and you're putting the electrons in at the cathode, and you're taking them out over here at the anode, the membrane is in the middle like a sandwich, and attached to the membrane is a catalytic material that's porous. It normally uses a platinum group metal like platinum or iridium or palladium, or some combination of them on both the anode side and the cathode side. And so what happens is the water, which is coming in here as feedstock, finds its way up onto the anode side, and the water reaches the catalyst and it dissociates, and the protons from the water go through the membrane. You can see these protons moving through. They look gold in the picture. And left behind are the electrons, which go to complete the electrical circuit. And here you emit oxygen with traces of water. On the other side, you have also water available, and the membrane has to be moist. But here the protons are coming through and they're combining with the electrons and recreating hydrogen molecules, which are leaving the cathode and produce the hydrogen product. And the electrolyzers, both the PEM and the alkaline, come in a lot of different sizes. Here are some of the products offered by Nel. They have small generators, medium size, large scale. The small generator might be something that could be used at the home scale or in a laboratory where the requirement is for small quantities. And the larger one would be used in an industrial plant, perhaps to make chemical products. This is a slide that's the courtesy of Innovate, and it shows the three different types of electrolyzers in comparison. First, the alkaline, and some of the advantages of alkaline is it's low cost. It doesn't have the expensive catalysts. It can work off of nickel, for example, instead of platinum. It has good efficiency, typically around 50 to 65% conversion of electrical energy into hydrogen energy. That's quite mature. This alkaline electrolyzer technology has been around for 100 years, so it's fairly well developed. It doesn't like to have the load low. It tends to have more contamination of the oxygen with hydrogen and the hydrogen with oxygen when run at low loads. And it doesn't like to adapt to higher input power and lower input power quickly. So its use with intermittent resources like solar energy and wind energy are not optimum. Generally, it's used in large systems where there's electricity available at a very low cost. For example, perhaps at a hydroelectric power plant. Some of the early large alkaline electrolyzers were operated at Niagara Falls, for example. The PEM has some advantages like dynamic response to wind and solar, and night and day diurnal operation is no problem with PEM. But as mentioned earlier, it has some expensive materials involved. The titanium is not as common here as you would find the platinum group metals. The efficiency of the PEM electrolyzers is not really lower than the alkaline. It's also probably in the neighborhood of 60, and at low current density, it could even be as high as 80% conversion efficiency. The places where you see this finding a fit right now is in production of hydrogen for refueling stations. Not so much in the petrochemical industry. In fact, you don't find the alkaline or the PEM in the petrochemical industry. There you would almost exclusively find steam methane reforming hydrogen production. But it would be a good fit for electronics and semiconductor plants, and it's a good fit for turning electric power into gas, which can be stored. The AAM is the new one, and because adapters provide this view graph, you could see that they want to make it clear what some of the advantages are. Right off, the membrane is much cheaper than the proton exchange membrane. It has very good efficiency, and it can respond dynamically and intermittently, which are the advantages with PEM and the disadvantages with the alkaline. and it's modular and scalable. In fact, some of the systems that use AEM consist of many modules that are hooked in parallel, both electrically and for the product. And you don't have an expensive catalyst. So there's still development going on, and a lot of improvement may still occur with this. That's an alkaline exchange membrane. Hydrogen can be classified in a number of ways by a color code system. And the color code system has to do with the source of the hydrogen, what it's made from. For example, on brown hydrogen would come from coal or lignite using steam reforming. It really is not SMR, but it's steam reforming. And that has a very high emissions because the hydrogen to carbon ratio of coal is very low. The coal contains hydrocarbons, but there's not that much hydrogen in coal. Gray, it has a better hydrogen to carbon ratio. It's 4:1. It's made from natural gas using the steam methane reforming. So that's a better source than coal to obtain hydrogen from an emissions standpoint. And blue hydrogen is where you use fossil fuels like methane and steam methane reforming, but you capture the carbon oxides and sequester them. Carbon capture and sequester is CCS. And some of the sequestration involves re-injecting the carbon dioxide into underground formations in active or expired oil wells. And there are a few demonstrations, but not very successful ones. Pink refers to hydrogen that's made by using nuclear electric power and electrolysis. Green would be electrolysis using any form of renewable energy. And another green form would be if it's made from biomass and the carbon is recycled. The use of biomass can be considered recycled on a global basis if you harvest the biomass and use it, and the carbon byproducts are reabsorbed in new green growth. One of the reasons that there's a lot of interest in hydrogen these days is because it is considered as a substitute for hydrocarbon fuels in vehicles. And one way that you can use it is in a fuel cell vehicle. Another way you can use it is an internal combustion vehicle that runs on hydrogen. In the fuel cell vehicle, there's a fuel cell that provides electrical energy by consuming hydrogen and air. So you'd have to have a hydrogen storage tank, and you have to have an air compressor. And usually they're put together with a battery that's used as an electrical energy buffer, so that you can have a relatively smaller fuel cell producing the electricity that's charging the battery, and then you're taking the energy to run an electric motor from the battery and the fuel cell. And the electric motor turns the electric energy into mechanical motion to run the wheels. So it could be used as a fuel in fuel cells that would run cars, buses, and trucks. It could be used in hydrogen internal combustion engines, a gaseous fueled engine. It could be used in turbines that were in aircraft, or it can be used in boilers to produce steam. But it can be used as a fuel as well as a or rather a petrochemical or electrochemical chemical starting material. And it's really the use of fuel that is the current activity globally. And there's a great deal of interest in reducing emissions from vehicles. Other applications for hydrogen can be for electricity production, heating, stationary power systems, portable, process heat. I think process heat is a place where a lot of hydrogen will find a home, and the steel industry and chemical industry can use green hydrogen in ways that will result in the same products being formed with much lower emissions. So the uses today are oil refining, hydrotreating to get more hydrogen into liquid hydrocarbons, to clean them, removing sulfur and nitrogen, for example. To make chemicals, ammonia contains 3 hydrogens for every nitrogen. And ammonia is very interesting as a fuel also because its ability to be a hydrogen carrier without carbon. In the steel industry, coal is used widely, and in the chemicals would include ammonia and also methanol, which is a very large-scale industrial chemical. Methanol has got 3 hydrogens in a methane methyl ion and 1 hydrogen in a hydroxyl ion. So there's 4 hydrogens in methanol and 3 in ammonia, whether it's green or made from some other source. The thing about methanol and ammonia are that it's a lot easier to store and transport than hydrogen as a gas or a liquid. And there's a lot of infrastructure for the use of hydrogen carriers like ethanol and ammonia. There's pipelines and trucks and storage vessels, railroad tank cars, lots of ways of transporting ammonia and methanol that are currently in use. It's just that the sources of those 2 industrial chemicals is generally not green. Home uses, this is an area that really interests me personally, is that in the home, it can be used as a substitute for natural gas and also a substitute for electricity. Be used for heating, cooking, and backup power, for example, using a fuel cell. And it can be used for other things like welding and cutting. In place of, for example, an oxyacetylene torch, you could do welding and cutting with an oxyhydrogen torch. There's a little bit of that being done industrial, but not too much with using hydrogen oxygen torches. So some of this is interesting on the home scale. And on the heating side, It's very attractive because it can be used for catalytic heating rather than flame heating. And the catalytic heating that takes place with hydrogen and air doesn't emit any significant amount of nitrogen oxides, whereas using hydrogen and flame does produce some nitrogen oxides when it's burned in air. Cars with internal combustion engines can have hydrogen as a fuel, but unless they use oxygen as well as an oxidizer with that fuel, if they use air, then they have to deal with NOx production as a byproduct in the exhaust. And there's demonstrators right now that use combustion engines and are dealing with the correction of exhaust emissions using the same kind of technology that's used for reducing emissions on hydrocarbon engine catalyst exhaust. So some of the fuel cell types are very similar to what you find in the types of electrolyzers. And in fact, back in the early days of the discovery of electrolysis, they found that you could run the electrolyzer backwards and produce electricity and have a fuel cell. They weren't optimal for acting as a fuel cell, but one of the good examples that you can find with electrolysis is that if you have an alkaline electrolyzer and you run that alkaline electrolyzer, it'll first charge up the electrolyte in the electrodes, just like a battery. And after a while, the battery is charged and you start to gas, which means that you're producing hydrogen and oxygen off of that electrolyzer. If you stop those and sorry about that. If you stop the electrolyzer, you could draw power off of that electrolyzer in the case of an alkaline unit. So that's how they discovered fuel cells in the beginning. The polymer electrolyte membrane fuel cell has the same kind of solid film electrolyte as the PEM electrolyzer. And the alkaline fuel cells can create electricity, but they're sensitive to carbon dioxide in the air. If you have air entering an alkaline fuel cell, the carbon dioxide can form carbonates in the electrolyte and make solid deposits. So that has to be a consideration. But they're very low cost because they don't have the PEM solid fuel and they don't have the expensive catalyst.
Walt, you just need to go faster a little. We'll run out
What
of
was
time
that,
otherwise.
Harry?
We'll run out of time otherwise. Go a little faster, please.
I'm sorry, I can't hear you.
We'll need to go faster, otherwise we'll run out of time.
Okay. Molten carbonate fuel cells run at high temperatures and solid oxide fuel cells run at high temperatures. The proton exchange membrane fuel cell is shown here in a diagram, and the fuel goes into the anode where oxygen would come out of the anode on a electrolyzer. So they go in the opposite side in terms of the electrodes. But they have air going in or oxygen going in and fuel going in. And this is what the basic circuit is like. And this would be the load that you would operate off the electricity made inside the PEM. Transporting can be done with cylinders, tube trailers, as a liquid, and in pipelines. This is a picture here of a tube trailer that might be brought to a compressed hydrogen station and used to feed dispensers to dispense high pressure gas. Hydrogen's a much safer fuel than gasoline, diesel, and natural gas as long as it's not in a confined space. I'm talking here more about leaks than anything else. If you have a hydrogen leak, it can dissipate and leave the leak site easily. And so most hydrogen plants are out of doors for that reason in case there's a leak. It's not toxic or poisoning. And because it's so light, it's even lighter than helium balloons. Helium's a mass of 4, hydrogen molecules a mass of 2. So it escapes easily and moves rapidly away from the source. Hydrogen that's I think gasoline and propane and natural gas are more dangerous because they hang around the source of the leak, especially propane. I've seen cases where propane leaks cause explosions because they traveled along the ground level and found a source of ignition and caused an explosion or fire. Most of the use today is in the industry, and the safety standards make it possible to use it safely, and industrial uses of hydrogen are well controlled and conducted by trained technicians and engineers. So it's generally pretty safe to be used on an industrial scale. But at the home scale, the safety precautions are not as well under control. So it should be used in well-ventilated areas so you don't get a combustible mixture, and you should not ever store mixtures of hydrogen and oxygen. Some people are using mixtures of gas that are called Brown's gas or Rhodes gas, and they're very dangerous to store. You can create them and use them at the site of production for welding and cutting and that sort of thing, but they're not to be ever stored. Even a small percentage can be flammable. It has very wide combustible limits of flammable and explosive limits. Harry, you want to say a few words here?
Yeah. I'm going to just show you a few slides, folks. And Walt, each time since you're showing the presentation, each time I'll ask you to forward the slides. So go to the next slide. Okay, so I'll make you familiar in a short time with the tremendous opportunities. United States, the federal government has funded $8 billion for clean hydrogen hubs through the Inflation Reduction Act. The California hub is ARCHES, which is Alliance for Renewable Clean Hydrogen Energy Systems. The funding for California is about $1.2 billion, being matched by the state. This funding is becoming available mainly through the California Energy Commission, but also through California Air Resources Board, CARB, and CAISO, which is the independent operator. It does need to reduce greenhouse gas emissions. In order to do that, all of it needs to be green. Hydrogen can store a lot of renewable energy, so it is a great economic and environmental opportunity. Next slide. So the current prices of hydrogen are through SMR and fossil fuels is about $2 to $3 per kilogram. Green hydrogen according to DOE, should be at $6 to $10 per kilogram. Unfortunately, at refueling pumps in California, the price is something like $30 to $35 a kilogram. Hydrogen prices of about $3 to $5 per kilogram will compete with gasoline. Those are kinds of some of the projects that I'm working on that to aim at that. Wholesale prices are a little bit lower. US gives significant price credits. California low carbon fuel standard is provided by CARB, California Air Resources Board, of $1 to $3 per kilogram. The US Department of Energy gives credits are similar. Um, so you can get somewhere between $3 to $5 in credit. So if you're making hydrogen at something like $8 a kilogram, the price can come down to the customer to be $3 to $4 per kilogram after the customer takes advantage of those credits. The U.S. government hydrogen shots has actually the federal government has these Earth Shots programs. Hydrogen Shots is one of them. The Earth Shots is all the environmental things they need to do for climate change. The Hydrogen Shots program aims at $1 per kilogram for green hydrogen by the year 2030. There's still a lot of challenges ahead for that. The prices of hydrogen fuel and hardware are a lot lower in China. Next slide. So the hydrogen use is expanded. The current production is 97 million metric tons globally. The issue is that greenhouse gas emissions are 930 million metric tons of carbon dioxide equivalent. This is projected to grow to about 500 million metric tons by the year 2050. I personally think my calculation shows that we need about 1,500 million metric tons in order for it to act as a solution to climate change. About 40 plus nations are in a very competitive race. There's a lot of competition going on into terms of who wants to be the leader. Chile, Saudi Arabia, China are leading. The US is ramping up its competition with its investments. California, of course, is leading among the states. It has the most number of refueling cars, buses, and trucks. The Intermountain Power Project is a big project, replaced a Utah coal power plant, which was already demolished, and it's using renewable energy, solar, wind, geothermal, and hydro to produce hydrogen, and is storing it in large stalled caverns. That part of it has already been funded. And then the electric power production, the first is a 30% blend of hydrogen. The Mitsubishi has already delivered the gas turbines for that and will deliver the pure hydrogen gas turbine after development. The main customer for that is the Los Angeles Department of Water and Power. This slide here is from the Mitsubishi Power company. The next slide basically gives you a list of all the business opportunities that are there. A large utility scale solar can produce hydrogen. It can be piped. Smaller modular scale based decentralized production produce hydrogen at site. Hydrogen production can be, of course, by other green methods, biogas and biomass. Technology innovation, electrolyzers is fuel cells and other things are going on in all sectors. Solar battery hydrogen power plants can be used to produce and renewable energy power. You produce hydrogen during the day and use it at night. Smaller scale power plants can be used for EV charging, for generating electricity for electric vehicle charging and hydrogen vehicle refueling. There can be home uses of hydrogen for cooking and heating. A lot of development needed there, but that's a significant business area. The innovations are taking place in the production of green ammonia and methanol, which are called derivatives. Next slide. So anyway, this has been our solar battery hydrogen incorporated has brought you this hydrogen training. We will bring you in future classes on all aspects of hydrogen. production, electrolyzers, fuel cells, storage, transport, power production, vehicles, ports, and home users. Anyway, this is our ends of presentation. Our next slide. Basically, thank you very much. And if you have questions, I guess we have one question, Walt. Again, from Mahmood, it says, thank you for the great presentation, but he's got to go. I don't see any other questions. Does anybody have a question they want to raise their hand? And they can raise their hand and we can ask the questions, answer questions. Otherwise, we are actually pretty close to getting done. I just want to say to everybody that hydrogen represents an enormous opportunity. It can be a major solution for climate change if you store large amounts of renewable energy. But the entire hydrogen industry is exploding now. If all that infrastructure gets developed to produce it, transport it, compress it, store it, and all the end uses for it, then you can basically use it to develop the infrastructure, and then that will produce an explosion in the use of hydrogen. And that, like I said, we are working on developing projects. We're working on innovative solutions that would reduce the cost of hydrogen, decentralized production closer to the source, because if you use solar energy, you can produce it pretty close to the end user. And then the third aspect is to work on innovative hydrogen um, solutions. And of course, the last part is we are having these hydrogen classes. So we look forward to educating you on all different aspects of hydrogen. Thank you very, very much. We have, I guess, one other question showed up. Again, thanks for the presentation. Most of it are thanks. We thank you very much. We will provide you personal access to all the attendees as well as the people who missed it. If they were not able to show up, we will provide access to recorded video, and that will be only for your consumption and not for distribution. So we hope that you will use it to run it and educate yourself as and when you're needed. And so again, thank you very much, and goodbye. And we hope this class was of great use to you. We have three thank you comments from Mohammed Tehami. He says, great presentation. Raj Banerjee says, thanks for the presentation. And how does hydrogen compare with batteries for dispatchable power on site? Do you want to, that's the only question I see. Walt, you want to try and address how it compares with batteries, dispatchable power with batteries on site?
Let's see. I'm not seeing the question.
The question is from Rogers. How does hydrogen compare with batteries for dispatchable power on site?
Oh, okay. Well, I think if you look at use on site, depends a lot on scale. In the home situation, you certainly could supply energy to home with batteries, and you could certainly supply energy to a home with hydrogen. At the present state of development at the home scale, it's probably a simpler matter to supply the energy with a battery. As you go up in scale, the use of hydrogen for a battery becomes more attractive. If you go up to the scale of a vehicle, one of the attractions of using hydrogen in a vehicle is that you can refuel it quickly. You don't have to wait for hours to charge the battery. But there's development going on both sides, both battery side and the hydrogen side. I think cryocompressed hydrogen, where you use liquid hydrogen to get the pressure without using compressors, is a very attractive area, and it's probably the best technology right now in order to refuel vehicles, both cars and trucks. And I don't see batteries as being a very good solution for heavy duty trucking because the weight of the battery is so large and the recharging time ties up the vehicle where it can't be in service. So hydrogen, I think, is a very good option for use in heavy duty vehicles.
Also, the hydrogen batteries are typically between 2 to 4 to 8 hours for energy usage, whereas hydrogen you can store it and you can use it at any time thereafter once you have stored it. So I hope that answers your question. Okay. Walt, did you want to add to that, or should we wind up?
One more that I'd like to share that I think is an important one. I'm going to bring that up right now. And that is to make the point of what the flammability and explosive or detonation limits are for hydrogen. And it's a real factor in dealing safely with hydrogen. If you look at hydrogen and air on the far left, and you look at the volume percent of a mixture, you can see that it will either burn or detonate anywhere between 4% in air and 75% in air, which are very wide flammable and explosive limits. And if you compare that with gasoline, that's over on the left here, you can see the gasoline has very narrow combustible and explosive limits. In an engine, it'd be very easy to use the hydrogen. It's sometimes more problematic to use gasoline in an engine because of the ability to start it when it's cold, or the vaporization of the gasoline causing vapor lock when it's hot. But of course, this is the widespread fuel of the present day. And another one that's interesting is propane. It has similar flammable and detonation limits as gasoline and methane, which is the main ingredient of natural gas. These are all in air. If you look at the far right, you can see that there's a mixture of hydrogen and oxygen, and there the explosive and flammable limits are even greater. So that's the big difference between hydrogen and most of the hydrocarbon fuels. I thought that was something that can be emphasized, so I'll leave it at that.
Okay, thank you very much. Again, we will get back to you and certainly look for feedback from you as to what you think about it. And then also we will make the video available to all of you. Thank you very much. And we